This report discusses a model for predicting the severity of bronchial asthma in children, the foundation of which is a neural network. Bronchial asthma holds a specific place among allergic diseases. Currently, due to the rapid increase of asthma incidence, this pathology can be considered as a global medical problem. Development of approaches in the disease treatment, as well as new medication creations, did not allow consolidating control over bronchial asthma. The purpose of the study is to develop a method for predicting the severity of bronchial asthma based on the use of a large number of factors for prediction. To understand the heterogeneity of the disease and identify asthma subtypes, researchers M. Deliu, T.S. Javush, M. Sperin et al. Used cluster analysis based on the definition of four distinctive features: age of onset, allergic sensitization, severity, and exacerbations in the previous year. Authors M. Lovrick, I. Bennick and al. used neural network-based models to predict treatment outcome in children with mild to severe asthma based on changes in asthma control, pulmonary function, FEE1 and MEF50 and FeNO values after 6 months of controlled medication use. The research paper by M. K. Ross, J. Yoon, A. van der Schaar, M. van der Schaar presents machine learning algorithms for detecting asthma phenotypes and predicting clinical outcomes, allowing for finding heterogeneous relationships between clinical features and outcomes. In the work N. A. Malfino, G. Turkatel, D. Riskin, a review of machine learning algorithms for predicting asthma exacerbations was carried out, allowing to identify the characteristic features of the course of the disease. Asthma prediction from common blood biomarkers using an affinity graph enhanced classifier improves asthma prediction accuracy compared to 5 state-of-the-art prediction models. Using an automatic machine learning model, a prediction model for severe asthma exacerbation was developed. The presented model demonstrates the ability to identify children who are not at risk of exacerbation. Data from retrospective electronic medical records of patients were used to determine symptoms of asthma in children in pediatric hospitals in China. To demonstrate the methodology for constructing a model based on the use of a neural network, we will use the results of a clinical study of the severity of bronchial asthma in children of the Kharkiv region in 2017. The asthma severity analysis group included 90 children aged 6 to 18 years. The structure of the group was as follows. The main subgroup included 70 children with bronchial asthma. The control group, 20 healthy children. Analyzed the data of a survey of parents about the symptoms in patients characteristic of bronchial asthma, as well as the history of the disease of the patients. During the analysis, 142 factors were considered. The aim of the study is to develop a method for predicting the severity of bronchial asthma based on the use of a large number of factors for prediction. A multi-layer perceptron with an architecture containing a single MA1Z and two M1, M2Z hidden layers when M number of input factors in the prediction model, MK number of nodes in K hidden layers, Z number of nodes in the output layer. The architecture of the neural network is shown on the slide. The values of the neural network nodes are calculated in accordance with the system of equations. The numerical characteristics of the selected sets of factors in accordance with the criteria are given in table. The calculated values of correlation coefficients between the model factors as well as between the model factors and the observed value are also presented in table. When building the prediction model, the sample for training the neural network is divided into two sets of data. The first dataset directly serves for training the neural network and makes up 80%. The second dataset, test dataset, which makes up 20%, is used to verify the prediction accuracy. The training process of the neural network with different architectures is shown on the slide. Table 3 shows the comparative analysis of the training results of the neural network with 1 and 2 hidden layers and different number of nodes in the hidden layer. When carrying out the comparative analysis, the random sequence of numbers used in the initialization of the neural network weights was a fixed sequence of numbers. As would be expected, increasing the number of nodes for a neural network with both 1 and 2 hidden layers results in a significant decrease in MSE. To quantify the quality of prediction of the severity of bronchial asthma cause, table on the slide 11 and table on the slide 12 present the prediction values obtained for a model based on a neural network with 10, 15, 4 architecture consisting of an input layer with 10 nodes, output layer with 4 nodes, and one hidden layer with 15 nodes. The severity of bronchial asthma cause was correctly predicted for 70% of the patients from the test dataset. This is an encouraging result compared to studies based on a linear regression model. Conclusions. The dependence of MSE value for training and test data set at different values of nodes in hidden layers has been analyzed. Increasing the number of nodes in the hidden layers of the neural network leads to a decrease in MSE and an increase in prediction accuracy. A comparative analysis of MSE values for the model using linear regression equations for prediction and neural network-based models is presented. The developed model for predicting the severity of bronchial asthma, the foundation of which is a neural network, allowed to correctly determine the severity class of the disease for 70% of patients from the test dataset. For the remaining 30%, the model predicted the results as a neighboring severity class. The results of further research is to investigate the dependence of the number of regressors of the model on the accuracy of the results of predicting the severity class of bronchial asthma. Thank you for attention.